Hi all, in this video I am going to discuss singularities of a complex valued function. Consider a function f of z whose Lorentz series expansion is given as a0 plus a1 into z minus z0 plus a2 into z minus z0 whole square plus etc. plus b1 by z minus z0 plus b2 by z minus z0 whole square plus b3 by z minus z0 whole cube plus etc. Now this Lorentz series expansion is divided into two parts. We call this as a regular part or analytic part because there is no singularity in these terms. So we call it as a regular part. The function fails to be analytic only in these terms when denominator becomes 0. That is, when z is equal to z0, the function fails to be analytic. So this part is called as a principal part. Here the function fails to be analytic, but in regular part the function is analytic. In principal part the function fails to be analytic at z is equal to z0. So z equal to z0 is called a singularity. Now based on the principal part, we are going to classify the singularities as three types: essential, removable and pole. Now if the principal part contains infinite number of terms, then we can say z equal to z0 is called the essential singularity. Now what if your principal part contains no terms, that is the principal part is absent? So z equal to z0 is called a removable singularity. If the principal part contains only finite number of terms, that is we can only count the number of principal terms. Say we have only m number of terms, then we can say z equal to z0 is a pole of order m. If m is equal to 1, then we can say the singularity is a simple pole, that is principal part contains only one term. If principal part has only one term, then we can say z equal to z0 is a simple pole. Now let us solve some few problems. Find the nature of singularities of the following function: f of z equal to e raised to 1 by z. Now let us first express this function in terms of Lorentz series expansion, making use of this binomial expansion. So f of z can be written as 1 plus 1 by z by 1 factorial plus 1 by z whole square by 2 factorial plus etc., which can be further written as 1 plus 1 by z plus 1 by 2 factorial into 1 by z square plus 1 by 3 factorial into 1 by z cube plus 1 by 4 factorial 1 by z raised to 4 plus etc. Here you can see the denominator has the powers of z, that is infinite number of principal part. So all these are principal part. So in infinite number of principal terms we have, therefore the function fails to be analytic at z equal to 0. Since principal part is infinite, we can conclude z equal to 0 as essential singularity. Now let us discuss our next question. F of z equal to sine of 1 by z minus 1. We are going to make use of this expansion and then convert this function as Lorentz series expansion. So here instead of z we are going to replace by 1 by z minus 1. So 1 by z minus 1 minus 1 by z minus 1 whole cube by 3 factorial plus 1 by z minus 1 whole raised to 5 by 5 factorial minus etc. I am going to rearrange these terms. So 1 by z minus 1 minus 1 by 3 factorial into 1 by z minus 1 whole cube plus 1 by 5 factorial into 1 by z minus 1 whole raised to 5 plus etc. You can observe we have the term z minus 1 in the denominator. We have infinite number of terms in the denominator, and all these are principal part because we don't have numerator terms z minus 1. Therefore, since principal part is infinite and the singular point here is z is equal to 1, so z is equal to 1 is called a essential singularity since principal part is infinite. Now let us discuss another problem. F of z equal to z into sine of 1 by z. Now again let us write the Lorentz series expansion of this by making use of this expansion where z is replaced by 1 by z. 1 by z minus 1 by z cube by 3 factorial 1 by z raised to 5 by 5 factorial minus etc. Okay. Now upon opening the brackets and simplifying further, we get 1 plus 1 by 3 factorial, sorry it is minus 1 by 3 factorial into z square 1 by 5 factorial into 1 by z raised to 4 minus 1 by 7 factorial into 1 by z raised to 6 plus etc. Here also if you observe, we have the denominator terms infinite. We have z square, z raised to 4, z raised to 6 etc. We have infinite number of terms in the denominator. Okay. So we have principal part as infinite, and here z equal to 0 is a singular point, and since principal part is infinite, we call z equal to 0 as essential singularity since principal part is infinite. Now let us discuss next question. F of z equal to z minus sine z by z cube. Here also we are going to make use of this expansion to find the Lorentz series expansion of the above function. I am writing 1 by z cube separately. Z minus sine z can be written as z cube by 3 factorial minus etc. Now upon opening the brackets and simplifying further, plus etc. So here z and z minus z get cancelled, so we get 1 by 3 factorial minus z square by 5 factorial. The next term will be z raised to 4 by 7 factorial minus etc. Here you can observe we don't have principal terms, that is we don't have denominators in the powers of z. Okay, all the powers of z are occurring in the numerator. Since principal part is absent and you know z equal to 0 here is a singular point, so z equal to 0 is considered as removable singularity. Now let us discuss our last question. Here we are going to make use of e raised to minus z expansion to expand our numerator. F of z equal to 1 by z cube, make use of the expansion where z is replaced by z square. So 1 minus z square by 1 factorial plus z square whole square by 2 factorial minus z square whole cube by 3 factorial plus etc. Now after opening the bracket and simplifying further, we get 1 by z cube minus 1 by z plus z by 2 factorial minus z raised to 6 by z cube. So, z cube by 3 factorial plus etc. Now, if you may observe, we have only finite number of terms in the principal part. That is, only these two terms are there in the principal part, because all the powers of z are in the numerator. Except the first and second term, all the powers of z appear in the numerator. So, this is our principal part, and principal part is finite, and it contains only two terms, n is equal to 2, and here the singular point is z equal to 0, and since it is finite, therefore we can conclude z equal to 0 is a pole of order 2. Now, let us discuss last question. F of z equal to sin z by z minus pi the whole square. Here z equal to pi is the singular point. So, we are going to expand this function f of z about the singular point z equal to pi. That means, wherever we have z, we are going to replace it by z minus pi plus pi. So, in the numerator, we are going to write sin z as z minus pi plus pi, adding and subtracting pi in the numerator, divided by z minus pi. Now, we are grouping these terms together. Always group z minus pi together. And also you know that sine of 180 degree plus theta is minus sine theta. Therefore, sine of pi plus z minus pi is nothing but minus sine z minus pi. Here theta is z minus pi. Now, our numerator becomes minus sine of z minus pi divided by z minus pi. Now, we are going to make use of this expansion, sin z expansion in the numerator. So, sin z becomes minus 1 by z minus pi, open the bracket, we are going to expand it, z minus pi minus z minus pi whole cube by 3 factorial plus z minus 5 whole raised to 5 by 5 factorial minus etc. Okay. Now, open the brackets. So, you will get minus 1 plus z minus pi the whole square by 3 factorial minus z minus pi the whole raised to 4 by 5 factorial plus etc. Here you can see that the powers of z minus pi, okay, all are in the numerator. There is no terms in the denominator. Since z minus pi occur only in the numerator, that means here principal part is absent. There is no principal part. We have only regular part. Therefore, z equal to pi is considered as a removable singularity. You can make use of this example for removable singularity. I hope you have understood. Thank you.